Okay, I'm Kent. It's nice to be here. I did my PhD at the University of Waterloo in the Institute for Quantum Computing. I'm all the things I'm going to talk about today. Are a bit away from what I researched. I like Noah worked in an optics lab during my PhD, but being in an institute called the Institute for Quantum Computing, you kind of absorb some things. So I'll try to share that with you. Nice to hear everybody's sort of general interest or first experience with the words quantum computing. I hope I answer some of your questions. If not within the hour, then we can chat afterwards. But or I'm always around this building if ever you want to come find me. So we're just going to start. It's going to be very basic. I picked hopefully an easy example of something to go through that should display some of the excitement about quantum computing while hopefully not chasing you away. So we're going to start with just what are some of these words, kind of dispel the mystery of the word quantum. We're going to talk about bits in your computer versus quantum bits, and then we're going to talk about quantum gates, how to actually do the operations in a quantum computer. And that's mainly going to be matrix multiplication. So if you're comfortable with vectors and matrices, that's what we're going to be doing. And we'll jump into Python for a bit and just set up some matrices and show you how these vectors evolve. We'll talk about what it means to measure. And then I'll take you through a search algorithm called Grover's search algorithm, which is why Grover's on the screen here. And we're gonna go through the easiest case, and then if time permits, I'll just stop myself with 10 or 15 minutes to go. We'll head to the IBM website and try out one of their quantum computers that you can access online now. Okay, so I need to go into full screen mode here. Yeah, so good? Not good. Hey. Okay, so maybe some of you saw a clip from a year or two ago of our Prime Minister standing in front of a chalkboard at the Perimeter Institute in Waterloo talking about quantum computing. I'll just read out this quote. And we'll kind of address some of the things he says and talk about if he knows what he's talking about or not. So he said, very simply, normal computers work well, either there's power going through a wire or not, a 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. So as a quick reminder to everybody, what does he mean by electricity going through a wire or not, a binary system? Here's a reminder of just what some of the gates in your computers all in front of you look like. You either have electricity going through it, a 1 or not, a 0. And you can do gates on your bits. So you can do the NOT gate, which just reverses the value, changes a 0 to a 1 and a 1 to a 0 and vice versa. And eventually you need to compare two bits to do any kind of computing. There's an AND gate, and the truth table on the right looks like this. It only outputs a 1 when both bits are 1. And then we have the OR gate, which when either of the bits are 1, it outputs a 1. So what is a quantum bit then? Well, our Prime Minister said, it sounds weird just to like, all knowledge is coming from the state. So much more complex information. What does he mean by that? Well, here's a possibility of what he means. Instead of just a 0 or a 1, which we could think of as like north and south pole on a globe, on a sphere, a quantum bit is allowed to be anywhere on that sphere. So it could be 0, it could be 1, or it can be anything in between. We call it a superposition. So it could be it's really given by a vector on this sphere. So it could be on the equator and all around the equator. And what Mr. Trudeau means by complex is that it can actually have it can be a complex number. So if you remember the imaginary number I, that can appear in this vector. We're not gonna go there. Everything we'll talk about today will just actually be staying on a circle instead of using the full sphere. But it's still, we want to think about our qubit as a vector. So still much more complex than just a 0 or 1. We can have lots of different values. And I won't spend a lot of time on this now, but just so you have some kind of picture in your mind of what that looks like for a computer. You know, in your laptops, a bit is actually just electricity going through a wire or not. In a quantum computer, there are lots of different ways people are trying to build them. The way that I think about usually is with optics. So our pieces of information aren't electricity going through a wire, but they're particles of light flying through the air. And I would use the polarization of the light. So whether or not the way the photon is jiggling, the light is jiggling this way or this way as it travels through the air. I would call this a 0, and I would call this a 1. And we can use things in the lab called wave plates to go in between them and to rotate them and control them. So that's one picture of your mind when you think about a qubit. Another one is if you've heard of spin of an electron or a particle. Spin is a magnetic property of an electron, and it actually it looks exactly like this sphere. It's either pointing up or down or anywhere around, based on how you can think of it as a very small bar magnet. Okay, so now we also need gates for our qubits. So just kind of like the NOT gate, we have a gate that we'll call the X gate, which doesn't do exactly what we call NOT, but it just flips the vector about an axis, about the x-axis, which is why it's called the X gate. So if we're starting up there, I'm going to use this. Don't worry too much about this funny notation that's called a ket. They'll pop up every now and then, but it's just to signify that something is a vector, a two-component vector like that alpha and beta. And this Greek letter psi is very commonly used in quantum mechanics because it refers to what's called a wave function. We're not going to talk much about that, but just so you know where that came from. Okay. Now it turns out actually we can't do a straight NOT gate like we can do on our laptops now, but we can just flip the vector about any of the axes that we want. So those are some of the operations that we'll do, is just taking the vector to different parts of the circle. So like I said, we have the X gate, and this will be represented by a matrix that looks like that. And you can imagine that if you were starting in the 1, so if your vector was pointing up towards the 0, the North Pole, the stick. Can't go too far. Thank you. So if we're starting on the North Pole, then if the X flips it about the equator, so we end up at the South Pole. We'll also have this gate that's called the Hadamard. That's just named after somebody. And it's represented by H. And that just takes you from a pole to an equator. And we have the Z gate, which you may guess from what I said before, that it's going to flip you about the Z-axis now instead of the X-axis. So if you're on the equator, it takes you to the other side of the world. You go 180 degrees around the world. Right. Yeah. Any questions like that so far? And lastly, we have the simplest thing, that's just called the identity, or just ID, and that just, it does nothing. It's going to leave your state alone. Everybody's comfortable with matrices and vectors, and we're on the same page. Sorry, Joel.
So this is not before you have a sphere, no.
Yeah.
Are these all in the same?
Yeah. So I'm just going to care about this outer circle of the sphere. We could talk about a lot more gates that would take you to like the three-dimensional part of that sphere, but it turns out that For the algorithm we'll talk about today, for the search algorithm, you actually don't need those parts of the sphere. But in general, yeah, there's a lot more places your vector can go, and you can always write down a matrix to take you from one to the other. Okay. And now, if you remember, we had an AND gate, right, or an OR gate, something that actually like compares two different bits. So we need something similar for qubits. We need something that's going to compare two qubits and make them influence each other. And this is actually, if you talk to somebody who works in quantum computing, or at least on the experimental side, this is the very hard thing to implement in a lab, to make two things talk to each other, two particles to talk to each other. But this gate is called the C-NOT. I didn't write it on the slide, so I'll just write it down here. Stands for controlled NOT gate. And what it does is we have a control bit, which is be in the top rail here. And when it's a 0, it actually does nothing to this bottom rail. So that'll be, this is kind of confusing, but here I'm using, this circle will be what's on the top rail. So if it's pointing up in the 0 state, to the North Pole, and so is the bottom rail, then nothing happens when we do our C-NOT bit. This stays pointing up and this stays pointing up. But now, if the control qubit, which is on the top rail, is in the 1 state, so it's pointing down, then, and we again started with the bottom one pointing up, then this is where the control comes in. It'll flip the bottom one to pointing down. So it flips it from a 0 to a 1, but only when it is a 1. Does that make sense so far? So that would be represented by this vector. And now, because we have 2 qubits, we have to write out a 4-component vector instead of a 2-component vector. So before, we just had 1 qubit. This was like the 0 state and the 1 state. I had like an alpha and a beta. But now, if we're going to have 2 qubits together, we have to write out 4 components, representing when they're both 0, when one of them is 1, when the other one is 1, or when they're both 1. And so that's what this C-NOT matrix would be acting on a vector that looks like this. Does that make sense so far, everybody? Joel.
So anything in these 2 states not change? Is it just that under the lowercase interaction? Or like if the arrow would be...
Yeah, so this is going to apply for, even if they could be pointing anywhere, and you're still going to act this vector on them. So if the control was pointing off in some other direction that wasn't 0 or 1, then that's where things would get interesting, right? So this is now neither 0 nor 1, but somewhere in between. And so you still act, and if you say, and your lower one is starting in the 1 state, so let's just do it out quickly. So let's say that this one is halfway in between 0 and 1, so it's got a little bit of both, and you would write it like that. And this one is in the 1 state. So now we have to write out, actually have to write out the full 2 qubit vector, which has 4 components. And it gets combined in a funny way. You have to you have to like put this into there, multiply this by each component. So sorry if this isn't obvious, but it's gonna turn into this. So this is again the 0 state and the 1 state. I'll just put quotes around them so you, because there's a lot of 0s and 1s. So this is the first qubit, and this is the second qubit. And now they're both together. This is the 0, 0, the 0, 1, the 1, 0, and the 1, 1. So we know And then we're going to act that matrix on this state. And so it's going to produce something else. It's going to give you this, I think. So I don't know if this is answering your question, but this doesn't just apply for when they're in the 0 or 1, because they can be anywhere in between. The C0 still, it actually, if your control qubit is somewhere in between 0 and 1, the C0 does somewhere in between nothing and something. Yeah. This is, yeah. Unfortunately, this is where we get kind of like hard to explain, because it's this is what we call an entangled state. And so we're actually departing from an analogy that you can use in the classical world or the regular world. How I went from here to here? Okay. I need some more chalk space. Sorry. So this is an operation. This is good because we're going to use this operation in the code. It's called a Kronecker product. So if my first state, if qubit A is in this state, and qubit B is in this state, I said, then the joint, the two of them together, there is a symbol like this, which just means that when you combine the systems, you put this matrix into each element of this matrix, and you do a multiplication. So what it's going to look like, we'll switch hands, is it's going to be 1 times this matrix. And again, we have the 1 over root 2. So this is really 1 over square root 2. And then again, 1 over square root 2 times the matrix. Does that make sense? And then you expand it out again. So I'm just going to pull out the 1 over root 2. And we have 1, 0, 1, 0. That's hopefully what I wrote before. Yes. No. Dang. Sorry, I got it wrong the first time. Oh, I started in the 1 state before. Gotcha. I understand the difference. Good. So then with this guy, then the C0, then you just multiply that matrix by this to get.
But first, why are we doing multiplication there? Aren't we doing 4? Isn't that?
It's a controlled NOT gate, so it's somehow like mixing the two vectors together. And it puts this thing called an entangled state. And the weird thing about the entangled state is we started with 2 qubits that we could think about as separate things, but after doing this gate, we can't actually think about them separately anymore. We can only think about them together as one joint unit. This is kind of like the magic of quantum entanglement. Does that make sense? Any other questions so far? Okay, next we're going to talk about how to measure qubits and what that means. So it's going to be, and you'll see this on the IBM computer, marked by a symbol that looks like this. This is just supposed to be some like measurement gauge and an arrow that points to a result. It's just a logo. But what it means is that when the qubit gets to here on the wire, it has to choose a value of either 0 or 1 at the end. So if we started, and I'm sorry I used this notation, I said I wouldn't, with this, we're starting with the state in 0. So on the top of the sphere, which is this vector, and we operate the gate H, the Hadamard, which is this matrix. So after that, the vector looks something like this, just 1 over root 2s. And then it goes into the measurement device. And what happens when you make a measurement is it outputs either 0 or 1, but it chooses it randomly. There's no way to predict what the device is going to say. But whatever the vector was before the measurement device determines the probability distribution from which the measurement device samples. I mean, the rule is you have to take the vector just beforehand and you have to square it, so that it turns this from what people call amplitudes into probabilities. So the probability of getting a 0 is 1/2. It's this squared, and the probability of the device saying 1 is that squared. It's also 1/2. So here we chose somewhere it was exactly in between 0 and 1. So the device is sometimes going to say 0, and sometimes it's going to say 1. And there's no way to know which one it's going to say. But we can know what the probability distribution of it choosing either looks like. Any questions on that? That's something that's part of the weirdness of quantum mechanics that people kind of don't like sometimes. This is a whole lot of whole problem. Okay. Whoops. What happened? Am I back? Not back.
Your screen
Stop sharing. How am I doing for time? 15 minutes. Okay, we're back. I'm not sharing, right? I just have to do this. PowerPoint. Okay, so here's another example of just of a circuit, and maybe we can just go through the whole thing. So if we start with we have 2 qubits, and both of them start in the 0. So if we wrote out their joint vector, both in 0 means you have a 1 up here. That's the 0, 0 state. And then we perform the gates. We do an X gate on the first one and a Hadamard on the second one. And then, so there's nothing after this point. They're still kind of, you can think about them separately. They haven't intermingled yet. But then we do the C0 gate, and then they intermingle. So it's maybe hard to see at first hand what the measurement will look like. So what we could do is we could jump over to Python, and we could just calculate it out with some matrix algebra. So let's go. Yeah, let's go over here.
So if you have Python data, finally you can type to your notebook.
Yeah. So be comfortable with that. So if we're, wait a bit so everybody's ready to go. But I'm just going to use NumPy for some in the matrix algebra. And the first thing we want to do is define the 0 vector and the 1 vector. So I'm just going to use the np.matrix. You could do this as a list, but because we're going to do a lot of matrix math, I found it easier to just do this right away. So we're going to say our 0 qubit is just this 1, 0 vector. And we'll call our 1 qubit this vector. Okay, and at the same time, let's set up what our initial state was going to be. So remember, we were starting with both qubits in the 0 state, but we want to write them as a joint vector. So I'm going to do that. I'm going to call the input state psi, psi. That's that Greek letter, and we're going to use the np.cron. That's the Kronecker product that I wrote out on the blackboard here. It's just going to do it for us. And so now what to do is we just input what the vector is for each qubit separately. So if they're both starting at 0, I'll just put in a 0, 0 in the Kronecker product. Let's just print that psi and make sure that's what we want. Yes. Okay. Now next we want to define the gates that we're going to use. So we're going to, in this one, we're going to use the X gate, the H gate, and the C0 gate. So again, let's type out these matrices. The X gate is a 0 and a 1 in the first line, and 1 and 0 on the second line. H gate, I'm going to just put the 1 over square root 2 to the side. Oh, that's square brackets. Okay, and the C0 is a bigger one. Okay. And next we just want to multiply the matrices. So you can use the dot product in NumPy for this. So first thing, remember on our circuit was we're going to multiply the first gates it sees are an X gate for the first qubit and an H gate for the second qubit. So we can actually do that easily with the cron command again. We have an X gate on the first qubit, an H gate on the second qubit, and then we dot the dot product with psi. Right. And now we've acted the first 2 qubits on it. And if we want, so let's just print that and see what that looks like before we move on. And equal, the vector is now either, it's a 1, definitely a 1 on the first qubit, which makes sense. It started with a 0 and then we flipped it with the X. And it started with the 0 on the second qubit, and now it's gone to an equal mixture of 0 and 1. Then that's 1 over square root 2 is that number. And now we also want to, let's call that psi 1. Now we want to do the C0. So now we just got that with our psi 1, and let's do that. The dot does this matrix multiplication. So why there's a dot and then the word dot, you have to ask the Python people, but
Is that like a math thing called dot?
yeah. Sorry, let's call this one psi 2 because we're going to use it again. So here's what it looks like. Actually just stays exactly the same. The C0 doesn't do anything to it. And that's actually because if you look at the C0 matrix here, you can think about this as when the control qubit, the first qubit, when it's in the 1 state, we rotated it down from the North Pole onto the equator. It's already lying on the x-axis, so it's not going to do anything to it. Okay, and now lastly, in order to see what we're going to measure, though, this is just what the vector is. We want to find our probability distribution. So we have to square it. And what we're going to use, because these are matrices, I'm just going to be safe and use the np.multiply command. And we're going to multiply side 2 with side 2. This is doing element-wise multiplication. And so what we get out is, oh, let's just print it to make it look nicer. What we get out are the probabilities in each of the states. And reading down, that's the zero. That's the zeros. The probability that the bits are 0, 0, 0, 1, 1, 0, and 1, 1. So we have a 50-50 chance of getting 1, 0, or 1, 1. Does that make sense for everybody so far?
This is not entangled state?
Not an entangled state, no.
So the information that we pass on would be the outcome of the distribution itself.
It'd be the distribution yourself is what would be like the quantum part of it. What we'll see in the next example is in order to actually do a task, we want to manipulate the probability distribution in some way that we get a high probability of the answer we want. So that when we do this measurement, even though it's like a random process, the probability of getting the right answer out is really high. And the thing is, because we're manipulating these vectors beforehand to kind of shape our probability distribution, these vectors kind of like, yeah, they manipulate, they interact with each other and certain components can cancel out. And we're going to see that in next. Okay, but we're going to try to do it quickly. Back to PowerPoint. Okay, so the task I want to talk about is called the Grover search algorithm. And the Grover search algorithm is asking the question, where's the rabbit? Which hat is the rabbit under? And maybe to you it's quite easy, but if the legs weren't poking out, it would be harder. We're going to do the example where there's 4 hats, but this would extend up to n hats, where n is some large number. And you're trying to find the rabbit. And you want to know, you want to find the rabbit, but what's interesting to us is how many guesses would it take to find the rabbit. So in the worst case here, if you just start from the beginning, it's going to take 3 guesses to find the rabbit. If the rabbit was in the 4 guesses, 4 hats to see the rabbit, but after 3 guesses, you know where the rabbit is. So that's good enough. So in the worst case, it takes 3 guesses to know where the rabbit is. Where you have the guarantee that there is definitely a rabbit. So that's the worst case. Obviously, the best case is the rabbit's under you pick right the first time. But if you take the expectation value, it's on average it's going to take about 2 guesses, a bit more than 2, about 2 1/4. We worked this out last night. But it's going to be about 2 guesses. If you played this game many times, you can expect that about 2 guesses to find the rabbit. What we'll see when we play this game with a quantum computer is that it'll only take 1 guess. Okay, so in order to do that, we have to set up some kind of circuit again. And it's going to look like this. We're going to start with 2 qubits. Because there's 4 hats, we can use 2 qubits because there's 4 states there, 4 vector states, 0, 0. So you can think about 0, 1, 1, 0, and 1, 1 as being the vector elements. So we're going to start with them both on the North Pole there. And then they're both going to come down to the equator with the Hadamard gate. So what that vector looks like is now an equal mixture of all 4 of these states. And then we're going to pass the state through the hats. And then the hats are going to have some effect on the vector we put through it. And I'll show you what that looks like. And then afterwards, we have to do some more gates to kind of do some processing before we do our measurement. So I'll take you through it. So after we do our first two Hadamard gates, our vector looks like this. It's an equal, every component has an equal probability. Now, if the rabbit was under the third hat, like in our picture, what the hat interacting your vector with the hats, let's say it does something like this, that only the state where the rabbit is has some effect on the two qubits. This is what computer science people would call this an oracle. It's like just some black box that you don't know what's inside, but you know it has some effect, and you're trying to use that effect. So basically, if we knew where the rabbit was to begin with, we would just send in this state. This is the state. This vector here, the third one, is where the rabbit is. But we don't know that ahead of time, so we're going to try all the possibilities. The hat box is going to just give us a -1 on the state that actually had the rabbit. And turns out this doesn't actually give away the answer right away, because it doesn't. The state comes out like this. And while this has a -1, this third component, it didn't actually. Remember, you have to square this vector to get the probabilities of measurement. And so it didn't actually change the probabilities. They all still have equal probability. So we can't just put it through the box and then measure right away and see where the rabbit was. Instead, we have to do something extra. And the extra thing we have to do is, after the hat box, we have our vector that looks like that. I'm going to call this group of gates W, just so it has a letter. It's actually going to, it's something that looks like this. And we'll be able to construct this out of the gates that I've shown you so far. What this W matrix does is, if we look at what it's going to do, is for every vector component, it's going to decrease the number, except for the case with the rabbit, in which it'll increase the number. So if we just took this W and did the matrix multiplication for this vector, magically we get out only probability where our rabbit is. Now, this is pretty incredible that it works in one step. If we had more hats, this would take a few rounds, and we'd have to redo the hat box and then do this W matrix again. But nothing would change apart from that. Eventually, the one component where the rabbit is would get big, and everything else would get small. So all the probabilities are going away, except the probability of measuring the one where the rabbit is going up. Sorry if that sort of.
We won't know where the rabbit is, correct?
We don't know where the rabbit is until we measure at the end, and we still
How did you choose that base W? Because that W is based on if you knew where the rabbit is.
But look at it; it's actually the same. And no matter where the rabbit was, if we had a minus sign here, it would do the same thing. You wouldn't get this data at the end; you'd get a 1 up here. But it's going to act the same way on no matter where the rabbit is. Yeah, same. Yeah, so that's important, because otherwise we'd have to know already where the rabbit is. But we can use the same W no matter which hat the rabbit's under, and what it'll do is it'll make all the other states shrink in probability, and the probability of finding the rabbit will go up. This only took one guess, yes, just because we're only doing this with 4 hats. If we had 8 hats, it would actually take 2 guesses. We wouldn't measure right away. We would do this whole thing twice in a row. So you'd check the hats, it would give you this -1. You do the W, your state would grow a little bit in probability, and then you do them again, and your state would grow a little bit in probability each time.
So it's like, basically you can only do 4 things at a time for every 2. Because you're saying, yeah. So if there's 2, and if you have 4 things to search, you only have to do it once. If you have 8, well, is every 4 in this case?
So have to
If
be.
you have 4 qubits, you could do it. You could do 8.
You had 4
8 hats with 1.
With 4, it actually goes squared. So if you had 4 qubits, there would be 4 squared components in your vector. So you could look at 16 hats. Yeah. So that's part of the nice thing, is that it only takes the amount of qubits squared is the number of hats you can look at. But the other takeaway from this is that if you were guessing, it would have taken you on average 2 guesses to find the rabbit. And now I'm telling you it takes only 1 guess for this case. If you had 8 hats, it would take you on average 4 guesses. And for the quantum computer, it would be able to do it in 2 guesses. And as you increase the number of hats, the number of guesses that you or my computer now would take on average is about n guesses for n hats, or n divided by 2. But it's going to grow in a straight line as you add more hats. But the quantum computer is going to take square root of n guesses, so it can do it a square root faster. So let me just write that down, I guess. As you increase the number of hats, the number of guesses is going to go in a straight line for me, but it's going to go square root for a quantum computer. So when there's a lot of hats, the bigger the database or whatever you're trying to search, the better it is. Yeah.
Yes. Does a guess take as long time as a guess?
It's a good question, right? Because it's not really clear what the guess is here. Before it was clear, like I'm picking up a hat, I'm looking under it, and is there a rabbit there or not? And here the guess is it has to do this matrix. So you have to have already some like quantum architecture, some interface with your database that can allow you to do this type of interaction. So that's not a trivial thing, and that's a good question.
Like that's implemented correctly?
Yeah, exactly. Okay, we're nearing the end, so I'm going to forego the back to Python part, and let's go right to IBM. And I'll show you the gate sequence we want to do. So for some reason, for me, this IBM website only works in Safari, or maybe in Chrome. But I upgraded Firefox recently, and it stopped working there. So did everybody get a chance to sign up or make an account on this? If not, it's you can do it at your own leisure. But I guess you end up at some website that probably looks like this. We want to click on the experiment button. So IBM has a whole department devoted to trying to develop quantum computers. And they're making them out of superconducting circuits, which I'm not going to get into now about how those work. But thankfully for us, they've just recently put up an online interface with some of their chips. So we want to go to Composer, if you're there already. And the first thing we see is this big blue screen. And it shows you what the chip looks like. So this chip has 5 qubits on it. And we have qubits 0, 1, 2, 3, and 4. And this shows you like how the wiring works. And basically what all this means for us is that anything that's connected by an arrow is what we can do those C0 gates between. So qubit 0 and qubit 4 aren't connected directly. So we can't do that C0 gate between 0 and 4. But 2 is connected to everything, so we can do 2. And you can get around this. I mean, if we wanted to do something very complicated, this wouldn't really hurt us. What would hurt us more so is that these gates still have errors in them. So in the real world, all these operations aren't perfect. And if you can only do them so many times before your information kind of bleeds away.
Sorry, why are arrows one way?
Are they one way?
Why is it like,
This might actually affect like which bit is the control and which one is the target in the C0. I'm not sure exactly. Yeah, I think that's right. I think that's it.
Isn't it letting you place a C0 on certain three?
Oh, okay. Sorry. They've also just more recently put up a 16 qubit chip. We're going to use the 5 qubit one because that's all we need. We only need 2 qubits. And there's another one on here that is 5 qubits, but that's under maintenance. Okay, so we're going to go to, if you're in the Composer tab and you just scroll down, we see this thing that looks like a staff in music. And that's probably why they call it Composer. But it's just our, and they call this a score if you want to save it. But it's just our circuits that we're doing before. So maybe you can see on your screen that all 5 qubits, they're going to start the circuit in the state 0. Now again, we're only going to use 2. And so if you remember the first part, the first thing we want to do is act the Hadamard on our qubits. So I'm going to use qubits 2 and 3, just because 2 had the most connectedness. And what you see on the right here are all the gates that we can do on the quantum computer. So we have the Hadamard, we have the X gate, we have the Z gate, we have the identity. This plus is the C0, and I'll show you how to set that up. We have the measurement, and we have some other gates that I didn't get a chance to talk about today. But if you go into their help section, it should give you good tutorials on how to use these things. So the first thing we wanted to do was act the Hadamard on both qubits. And I'm going to, somewhere I have the circuit written out. It might be actually on the Python, which will get shared afterwards. OK. And then, yes, this is what the Oracle matrix looked like. But I've told you it looks like a CZ, which is something I didn't define until here. The Oracle matrix is going to be a few gates. It's going to be, first we want, if our rabbit, we're saying the rabbit is going to be here, then we want to first do the Z gate with the identity, and then we want to do all these gates after it. So let's do that. Sorry, I'm the only one with access to this right now. So we want to do the Z gate on the first qubit. And you can put the identity on the second one or not, it doesn't matter. It shouldn't matter. And then we wanted to do the CZ gate right after, which is just all these gates in a row.
you actually have to put the identity on there?
You don't have to put the identity on there. If you and I should say, if you want to take if you place the gate somewhere you don't want to and you want to take it off, you hold it down. There's a delete, the little garbage bin up there. Oops. So next thing was Hadamard, and then the C0. So you want to place the plus on what the target is, and then drag the control. So I'm going to place it on qubit. Oh, it doesn't let me do it on qubit 3. Okay, so I made a bad choice. Let's see where we can place our C0. Oh, we can just reverse. Just reverse. We'll make qubit 3 the control, and qubit 2 the target. Okay, everybody with me there? And then, so that's our oracle. Now we need to do that W matrix, which I've written out down here, and it's a bunch more gates that look like this. So it's Hadamards, then 2 Z gates, and another controlled Z. So one thing that's good to remember about matrix multiplication is this is actually the gate that you want to put down first in your circuit. The qubit sees so back over here, we want to do, whoops, back over somewhere, not there, here. We want to do H and H. Then we're going to do our CZ again, which is these 3. So this is slightly redundant, all these H's, which is too bad. And then after that, I think we're doing Z and Z. Yeah, and then H and H right after it. No, they shouldn't matter. I think they'll collapse it all to one thing. Okay, except that now we have to scroll, I guess. That's the only. Okay, so that's the setup. I'll leave that there if anybody wants to catch up. Actually, I'll slide this over so that we can keep using what's left. And that's it. All that's left to do is measure. And so we have to tell the computer what we want to measure. So we're going to use the measurement logos down here. And we say we want to measure that qubit. And it's going to output it to this called the classical register down here. And same thing for that qubit. We want to measure it as well. Okay. And
So you can't measure it at the same time?
yeah.
It doesn't really matter.
Yeah, I don't think you can, but it doesn't really matter. So this is the whole circuit. So we're ready to go. Now, if you made an account, they give you a certain number of units. I think you get 15 when you start. I've got 5 left. So if you want to run the experiment on the quantum computer, it's going to cost us 3 units. These tabs, so run would run it on the machine, and there's a queue to use it, so it'll email you when it does it and show you the results. This tab here is how many times you want to run the same thing on the machine, just to collect some statistics. Because if there's a probability of all these results, you want to run it more than once just to see what the results are. So typically, what I would do is, I'd run it, but then if there's a queue, I would also push the simulate because it's not a hard circuit to simulate. So let's run it. I'll click run. It'll say, oh, you should name your experiment. So we'll call this Grover search with 2 qubits. Click OK. Confirming your execution. 100,024 shots. We found a result. Oh, I already made this code earlier, so it's telling me that why are you doing this? You already have the results. But if you did it, then probably didn't say that. So let's look at the results I got last time, just so that we don't have to wait for an email.
I'm also getting that, although I've never done it.
Really?
So that's because
Sorry?
is that because I think you can Yeah. Never run. Because that's basically. Yeah, it's that run. What's the same time?
I wonder if anybody who's done this exact thing on the machine, it's already saved it. I ran it yesterday, but it had a different date. But okay. Here's some results. They're hard to look at. So because there's 5 qubits, now we have a whole bunch of different states this could be. So we have to read these properly. But we were using we're using 2 and 3. But which one? Our first qubit was qubit 3, and our second one was 2. So it'll be the numbers we care about are these ones. Well, yeah, that we're reading these right. So we care about the second and the third number in this list. So we have like, blah, 0, 0, blah, blah, blah. And this is the list we care about. So we know our rabbit, well, we had set up our rabbit to be here. And so it's run it 1,024 times, and it's 85% of the time we got that result. So that's good. And then the other times it clicked we're on 0, 0, 8% of the time, 1% of the time on 0, 1, and then if we go all the way to 1, 1. And there's a whole lot of other options, but they never clicked because we never used them. Okay, so there you have it. Sorry, I went a bit over time here. But what we've done is we've used a quantum computer that's online right now. You can play around with it some more if you like and try out all these gates. I recommend their help file's very good. They have a tutorial on this algorithm that I showed you today, as well as some others. And they show you how to set up the circuits. I hope I dispelled some of your fears or about quantum computing. Sorry if I didn't, but just invoked more. But maybe we can chat more afterwards if you have questions. Thanks very much.